image here is one of our observatories. It's a high altitude observatory at Sonnenblick at 3,000 meters. And this is just to give you an impression what I mean by steep terrain. So we are looking at basic wind speed in steep terrain in this presentation. Basic wind speed is just something like the 50-year wind speed. I myself, I work at the National Weather Service since 2010. And since 4 years, I'm working on wind projects and on renewable energy. And I'm currently coordinating our team on renewable energy at Geosphere Austria, which is not only on wind energy, but also solar radiation, PV, and geothermal energy. Next slide, please. Here's just a quick overview of Geosphere Austria. I won't go on in detail on to all these bullet points. Well, we are a weather service. We do all the forecasting. We provide warnings. I might just highlight that we also operate our measurement network of MET stations, which are unfortunately all at a height of around 10 meters above ground, which is an WMO standard and not so useful for wind energy applications, unfortunately. And yeah, so yeah, just skip this and go to the next slide, please. Let's focus on wind energy at our weather service. So we have actually two groups. We have the wind energy forecasting, research and development group, and they are providing, well, they are doing research and providing products for power forecasting for turbines or wind parks based on statistical and AI methods. We do provide nowcasting information in very high temporal resolution, but also forecasts for the next few days. And they are really active in AI research, and they actually just were awarded a national award on technology and on AI, which is shown in this picture here. It's actually a link to this award. And if you're interested, you can also go to this website, which is the bullet point here, where they provide some information on their work. And we are also very active in the International Energy Association Wind Task 51, which is about wind forecasting. And the part where I am involved mostly is on wind energy consultancy. So we do standard services like AEP, site assessment, resource maps. And we are using WindSim, of course, but also WindPro and the WASP suite. And this is based on wind data. We use MET stations sometimes, and very often reanalysis data. And we are mostly working for locations in Austria, but occasionally also in other countries. What you see on this map here is Austria and the locations of our wind turbines in Austria. And as you can see, there are none, really exactly none in the western part, in the mountainous part of Austria, which you might know if you are likely to go skiing in Austria sometime. So it's really hilly and steep terrain, and so far there was lots of objections of putting wind turbines in these regions. Next slide, please. Okay, so let's look at some of the cases which we have where we are using WindSim beyond wind energy. And one of these cases is for cable cars. So we have customers like ski resorts, but recently also from municipalities who are planning and building cable cars. And for this, we apply WindSim to estimate lots of different parameters like wind speed, interaction along the cable car line, the pillars of the cable car. They're also interested in maximum wind speeds. We have provided also information on gusts, wind gusts. And yeah, we are also calculating warning and switch off times for these customers, depending on their warning limits and switch off limits of wind speeds. And quite often we also do an installation of a wind sensor for a year, like shown in this picture here on top of the mountain, which we then can use via MCP to have really local data for our WindSim simulations. We are also in contact with a European norm. I call it the cable car standard working group, and we are also providing expertise regarding wind for their applications. They are mostly interested in lateral wind speeds for their cable cars because they are interested in the how far each cable car is moving to the sides actually, and they might even be touching in strong wind gusts. So these are some work in progress. So this is one kind of application. The next one is on the next slide, which is on water reservoirs or dams. You can see an image how it might look like on the left. Here we also have customers from energy providers who are operating these water reservoirs, and there are also guidelines for which provide information of parameters they are interested in. So this is important for estimating the wave heights at the water dam and the pressure on the structure itself, I believe. And we are doing WindSim simulations to provide all these different statistics on the wind at their water surfaces. You see just a orography map of one of these cases with 3 water reservoirs, which we did, and it's just a WindSim graph on the right here. Okay, so this is also one of our applications, and the next is the core of the presentation actually. It is about calculating the basic wind speed. So what is the basic wind speed? It is the 50-year wind speed transferred to a height of 10 meters above terrain and for flat open terrain, which is called category 2 according to the European standard on wind actions and structures. And so we have customers who are maybe building a power line, like it is shown in this larger image here. This is just an elevation map. The black dots are the mast positions. And for this case, we're also running WindSim and transferring our climatologies to the mast positions via what I call fake turbines. So I'm placing turbines at these black dots and creating these power history files, and via an extreme value distribution, I can obtain the 50-year wind speed and then convert this to the basic wind speed via the roughness length Z0. This is all very well for few locations, like in this case, but we also have this idea in our heads that we want to create maps for larger regions of basic wind speed. And this is the next slide, please. We were actually facing a request from a customer for calculating a basic wind speed for a larger region, let's say, in the mountain valley in Tyrol. And they were interested really in having the basic wind speed information on a grid with on a horizontal resolution of about 50 meters. And so the target polygon is shown here in this image. It is rather large. It has 50 meters horizontal resolution of the grid cells, which yields about 280,000 grid cells. The altitude range in this area is from 660 meters to above 2,600 meters. So it's quite complex terrain. And so now our standard method is obviously not possible. First, because you can't put 280,000 transferred climatologies or fake turbines into WindSim. There's a limit. And this is very well that there is a limit, because we were also investigating on doing this transfer of climatologies ourselves, and we had huge support from WindSim, thanks to Can and the whole team, in understanding the algorithm of transferring climatologies. I didn't succeed, but anyway, it would not be possible with this huge amount of transferred or fake turbines, because if you look at one of our measurement station, which might have 20 years of data in 10 minutes interval, and this would yield processing of about 8.4 terabytes of data just to arrive at the 50-year wind speed. So this is just not feasible. And it's also not scalable to if you would like to look at larger regions. So we had to come up with another idea, which is shown on the next slide. Okay, so our, let's call it alternative method was to do WindSim simulations. Actually, a nested WindSim domain, two nested domains, one smaller domain nested in a larger domain. This was done not only because meteorologists like to do nested simulations, but because in the inner domain, we don't have a refinement grid. So this is just the inner domain contains of all grid cells at the same resolution, that is 50-meter resolution. And we also fixed the lower levels, vertical levels of our inner domain to certain values, which were necessary because they also represent the height of our measurements and of our target quantity, that is 10 meters above ground. Okay, next slide. This is the algorithm I used. So let's go through that. So we do a WindSim standard simulation. Of course, you need an elevation model and some roughness data. And when you do the simulation up to the wind fields module, you will receive all these speed 2D files per sector and per altitude in your results. And from this information, we went forward to calculate a speed up factor. A speed up factor relative to the position at our where we have our measurements, the MET station. So for each grid cell, we compute just a ratio of the speed for each sector compared to the speed at the MET station. And in blue, you can see here we have the MET station, which gives us a time series of 10-minute wind speeds. From this, we can calculate, of course, the 50-year wind speed via extreme value distribution. And we've done this per each sector. And then we go forward and just multiply for each sector the 50-year wind speed with the speed up ratio, which we just calculated beforehand. So we have at each grid point for each sector a 50-year wind speed. And our final 50-year wind speed is just the maximum across all sectors. So this was the very simple and pragmatic approach of arriving at 50-year wind speeds for each grid cell in our simulation. And on the next slide, you will see the result. Result is on the next slide, please. Here on the right, you see the in color code the 50-year wind speed in our target polygon. And this is ranging from 5 meters per second at low lying in the valley down there and reaching values up to 90 meters per second at mountain crests and mountain tops. And so I wouldn't say I was shocked, but it's a range which we didn't expect, because a realistic estimate from our experiences would be somewhere between 15, maybe 45 meters per second. But actually, nobody knows the 50-year wind speed at the mountain crest because there are no measurements. But this is something which we are guessing from our experiences. So we are receiving really extreme speedups at mountain crests and tops. And the possible causes for this are that our MET station, for once, is located at a very quiet place in this valley near Umhausen. It's rather in the middle of this image. And so there we get obviously very low speed to T values. And if you take the speed up as the ratio of each grid cell to this low wind speed value at Umhausen at the MET station, you will reach really high speed up factors. So this is one of the problems. And of course, this is a really raw approach and simplified approach where we just transfer the wind speeds and we do not account for any direction change whatsoever. So this was just the first step in our approach of obtaining the 50-year wind speed. So we had to go further, which is shown on the next slide. Yes. So we thought, well, we should make use of WindSim's ability to transfer time series via fake turbines, which definitely is a much better approach for few locations. So we placed 635 fake turbines into our polygon, equally spaced, and transferred the power history files to each of these stations, then calculate the 50-year wind speed at each position, and then again also the basic wind speed, the VB0, according to the standard, which is just a function of the reference length. So we get at each of these blue dots the basic wind speed, which we must regard as the truth values, which we do regard as the truth values. And on the lower left side is just the histogram of the values of the 50-year wind speed at turbine locations or fake turbine locations, which ranges between 5 and 63 meters per second, which is much better already. But we can also see that there are also some values which are not really realistic, let's say. But it's much better than the raw output. So on the next slide, we can see that we need to go one step further, which is a regression routine. So we regard the truth as truth, the basic wind speed at the fake turbine locations. And then I was looking for lots and many predictors which could describe how the wind field might look like in this polygon. First, of course, I take the basic wind speed grid from the previous slide. And then I took in some information on the terrain itself, like slope and aspect, the altitude, and two indices, the TPI and TRI, which are just indices representing the complexity of the topography. And I also took the GASP data, the Global Atlas of Sighting Parameters from DTU, which provides a 50-year wind speed at 50 meters above ground, and transferred this to basic wind speed, again via reference length. I also took the NEVA, European Wind Atlas, mean wind speed as a predictor. And then I just threw it all into a couple of regression routines to predict the basic wind speed between the points. And it turned out that the random forest regression, which is listed here first, gave the best results. And so I used this in my end result. And so we arrive at, let's say, an optimized basic wind speed grid or map, which is shown on the next slide. Yeah, so this is the final result. After some tuning and yeah, tuning also the results from the fake turbine positions, we ended up at this map, which gives wind speeds, basic wind speeds between 17 and 34 meters per second, which is something which we would expect. And you can see, or you can almost see that at higher altitudes, this mountain crests, of course, you have the speed up effects, and in the lower lying valley, there are obviously lower values. And on the right, you see a histogram, distribution of the basic wind speed values for several altitude ranges, and for lower lying locations, of course, you have lower wind speeds, and then for higher altitudes, it's rising. We also did a comparison with basic wind speeds from our national standard. It's called, well, next, yeah, which is called the Ö-norm. It just gives a rough estimation of the basic wind speed across Austria. And this is just a comparison where we see that we are, let's say, overestimating for low-lying terrains and underestimating for high-lying terrains. Okay, so I'm coming to my conclusions already on the final slide. Next slide. So let's say this was really a quick study from a customer. This was all done in about 3 weeks, I think. But nevertheless, we did succeed in deriving a realistic basic wind speed from WindSim. but with extensive post-processing afterwards. The problems I've already mentioned were the extreme speed-up ratios from the speed-to-T files, most likely because our met station is in a really calm area. And yeah, actually we are pushing WindSim a bit to its boundaries or its applicability, let's say, because we are dealing with measurements which are really at low sensor heights, which is usually 10 meters, maybe 15 meters. And from feedback from WindSim, I know that this is not really the best data you should use for your simulations. Yeah, extensive post-processing was necessary, of course, and the transfer time series via power history files gave more realistic 50-year wind speeds than my simple approach of calculating a speed-up ratio. Now, we are, as I mentioned in the beginning, we are also interested in doing this exercise on a much larger area, that is to say, for the entire domain of Austria, because we are in collaboration with the Austrian Standards Institute, and they are really interested in obtaining a basic wind speed map for the whole country. And I know that also other neighboring countries of ours are doing the investigations in this direction, but we are still not sure how we should approach it, and if what I've presented here is a viable approach, actually. With that, thank you for your attention.
Inga, thank you very much. Sorry for jumping slides here a little bit, but I thought it was a very interesting presentation. And for those of us with a relationship with skiing and hydro dams, it's good to see that also those are being looked after. Vincent, do you have any questions for Ingo there in the chat?
Yes, thanks a lot, Ingo. So we have one question from Anne, and it's a little bit long, but I will do my best to read it as clear as possible. So it's when using the speed up factors to calculate the V50 wind speed at each grid point, do you run the flow model with standard speed above the boundary layer at 10 meters per second, or do you run a model with a higher speed above the boundary layer to represent a more extreme case? I guess that may have an impact on the speed up factors.
Yes, thank you for this question. I did the standard settings in WindSim, which is not optimal, I guess. Yeah, so I took the 10-meter wind speed as boundary condition, and I might also not have taken the best turbulence approach. As I've seen today, as I've learned today, that there are better methods than the standard K epsilon approach in complex terrain.
Yeah, thanks, Ingo, for answering this. I guess this can be further discussed as well. So, yeah, this was the only question for it. Let me just double check the Q&A just to see that I don't miss any.
Yeah.
Okay, so yeah, that was the one and only questions for now. So thanks a lot.
Great, thank you, Ingo.
Thank you.
So we are then going to move on to the final presentation of today, and that is you, Ho, talking about the latest in MMC.